I have my pleasure of opening a performance in our discussion panel. I want to introduce our guests, Kylie Bemis from the Northeastern, Matloff from UC Davis, Jan Vitek from Northeastern, Luke Tierney from Illinois, and Tomas Kalibera from the Czech Technical University. I am leaving the panel, the panel to the panelists. Have a lovely discussion. Thank you.
Thank you. Hello, everyone. So my name is Kylie Bemis. I'm from Corey College of Computer Sciences at Northeastern University, and I'll be moderating the discussion panel today. And we have a really great panel of guests that I'm excited to hear from. So quickly, if I'm an author of a couple of packages on bioconductor, namely Cardinal and Matter. But really the focus today is on the panelists. And so I'm sure many of you are familiar with their work, but I think I'd like to start off before we jump into questions and answers to just quickly go through each of our panelists and have them say just a couple brief words on how they kind of came to working with R. I know we have some members of our core and some who are coming from a more research perspective. So I'll just go down my list. Tomas?
Yeah, thanks. So I started with R as a student of computer science. I had to learn some statistics and we used R. So I had to use R for some homework. And initially there was an option of using S plus or R. R was very new at that time, but it was fun because I could run it legally at home. Much later, I started using R for, I would say, real during my PhD for evaluating results of benchmarks, so data analysis in some way, both interactively and programming in R. And then much later, I was offered by Jan to join his team and work on FastR. You may have heard about FastR in Jan's talk before. So I started working with Jan on the Java version of FastR. And during that work, I was coming to the impression that there was no way that I could implement all of R in Java again. So I ended up interacting with Luke and contributing to the real R, and eventually I got to R core. So now I'm working on R. Yeah.
Great, thank you. Norm, how did you come to R?
Oh, well, okay. You know, I go way back. And when I first came to Davis, my students, probably a lot of people here can understand that when I first came to Davis, there were no computers, there was a mainframe, and that was it. It was a long time ago. And, eventually we got the personal computer and so on. And this language called S came in from Bell Labs. And I thought, this is really wonderful. We had worked with the BMDP package from UCLA, this again, very long time ago. And S really seemed like, this is really wonderful, a language actually devoted to statistics. So I actually got in with S, and then when R came out, well, this is really wonderful. It's a free version of S, so what could be nicer? And so the rest is history. It's come to dominate my life.
Thank you. And Luke, I know you've been working and contributing to R since very close, I think, to the beginning. Maybe you can say a few words about that.
Yeah, fairly close. First, I wish I was in Illinois because Illinois has a much better approach to COVID than we do. I'm in Iowa, at the University of Iowa. Yeah, I've been, when I used to be at Minnesota, we were one of the groups that had the S beta test agreement that let us run Bell Labs S in the early days. I was also involved with, I got into dynamic graphics and built a Lisp-based system called LispStat that modeled a lot on S, but using the Lisp syntax. And I guess late 1900s, I visited New Zealand and got roped into R, and I've been doing that ever since. So I've been an R core member since about the late 1990s. Work on it. Mostly I work under the hood, but there are a few top level things that I've done, like namespaces and things of that sort, and a number of things performance related, like parallel, the parallel package, the snow part of it, profiling tools, things of that sort. That's about it.
Thank you. I actually got into statistics because of my father, and who's also a statistician, and he's talked about using XLispStat back in the day.
That's good to hear.
Jan, so Jan is coming to us from kind of a researching performance in R perspective. Jan?
Yes. So yeah, I'm a computer science professor, and for me, R is an object of study, of wonderment, and sometimes horror. And I came to it about 10 years ago after having worked on Java, on real-time Java, having done work on type systems that ended up in the Rust language. And I thought R would be an easy summer project for maybe a year or two. And I'm still here.
Excellent. Well, we're definitely glad that you are still working on R. So to go into some of the questions that we have for all of you, we're talking here about performance in R, whether R is slow, where it's fast, how we can improve it, what users can do to get the most out of performance in R. And so one of the topics that comes up a lot is loops in R, and kind of one of the common benchmarks of performance is just writing some kind of for loop and timing it. And so I think one of the questions is, do you think loops are actually slow in R? And is there a way to improve that? Should people avoid using for loops, or is it more of a case of people using them incorrectly? Anyone wants to?
It's a question for Luke, actually.
Well, yeah, loops in R are fast. You put a loop that does nothing in its body, it's very fast. What's slow is if you're, I think Jan was using the micro operations terminology. If your body is doing a lot of micro operations, you're paying overhead a lot of the interpretation of the steps. The interpretation is what slows you down. You know, if you have 10 bootstraps, each one is taking a minute, you write a loop around that, there's absolutely no reason not to do it. Norm may know about this one. There's a cultural thing that, you know, things that get into the culture disappear very, very slowly. In the old days, early days of, I think it was a Blue Book S, the implementation of loops was awful. Even if you had an empty loop, it would take forever. So you never, ever, ever use a loop. Even S got rid of that long ago. And it might even have been Brown Book S that this was true. But this is one of those things where somebody says it and somebody repeats it, and it keeps on and keeps on and keeps on. And I don't know how much of the loops is slow people say about R is based on, oh yeah, you write a mini benchmark with scalar operations, and yes, that's slow. And how much is, I heard from someone something sometime. I think of it as very similar to, I heard from someone that writing Lisp is hard, so it must be. You can't beat it. Anyway.
Yeah, I remember.
Oh, go on.
Oh, sorry. Well, when I was still a user, so I had no skills to actually profile things. Like 15 years ago or something, I remember that I have improved performance of some of my programs by switching from for loops to sapply, right? So it may be about the time when people believed that for loops were slow, but of course it was way before the bytecode interpreter.
I mean, when I'm teaching people about, if you take scientific algorithms that are written in pseudocode or something, usually they'll be written at the scalar level. And it's a good first step to go to a loop, because it doesn't matter how fast you compute something if you're getting the wrong answer. You have to get it right. So first step, translate pseudocode to executable, and then profile it, time. If there's no problem, don't worry about it. If there is, then think about vectorizing your operations. And again, profile, time it, and don't spend any time worrying about it unless you've proven to yourself it's really worth doing. And the very last resort for me is going to put some of it into C, but certainly not until I've measured with profiling what is worth putting into C, because I don't want to spend any more time there than I have to.
Isn't there an old saying, something along the lines of optimization is your enemy? Old saying in the software area.
Yeah.
Yeah, we say that the premature optimization is the root of our evil or something. There are variations on this. This is true in many ways, of course. The obvious thing is that people usually end up optimizing things that take only a small proportion of the execution time in their program anyway, right? So if you speed up 10 times something that takes 1% of your execution time, you haven't won all that much, right?
Mm-hmm. Well, can anybody say what is there a problem? How many R users are really finding that their code is too slow?
That's a good question. Jan, maybe you could speak to that?
So, I mean, I can't necessarily answer that, but the other question that would be interesting to know is how many people in the R community were forced to learn C or C++, because either of actual or perceived performance problems. And that's something that one of the goals would be to push more code into R away from C++, because it's this, this firewall, and you can't inspect it. It behaves differently from your R code. So I think if there was an argument for speeding up R, it is, so you can write those loops without really having to worry about them.
That's always been the motivation behind the bytecode compiler, not any illusion that it would ever eliminate the need for C code, but just to move the point where you have to switch to C code to get adequate performance.
Speaking of the bytecode compiler, that's another topic that we have. So I think when the bytecode compiler first came out, it was certainly kind of a mini revolution. I'm not sure how many users, though, are actually even aware that a lot of the code that they run has been byte compiled. And so I suppose a question is, how often should users actually be aware of the byte compiler, and are there times when they should actually try to use it or call it explicitly?
My view is ideally they shouldn't need to know about it. Now that we switched, I mean, this was Tomas' work to do a lot of the cleanup needed to be able to make it run by default via the JIT, what we call a JIT. So, and I've really not seen any issues. I mean, occasionally we'll run across slight bugs of incompatibility between the two, and there are one or two known things where they're different. I think all the known ones, the bytecode behaves more sensibly than the interpreter, and at some point they'll get fixed. But mostly it happens automatically, and every loop is compiled, and so you're not seeing. Jan in his talk showed some benchmarks against the AST interpreter of loops. You're not going to see that anymore unless you ask for it. The default is you go through the bytecode compiler, and yeah, it's still slow, but it's not slow by 1,000. It's slow by 200. I'm just making those up. They're, but they're yeah.
Kind of a related question, and I think Tomas has presented on this in the past. Is there any ways or suggestions for how users can get the most out of the byte compiler?
Well, you know, I wanted to ask everybody here, excuse me, in Julia, I've heard, I don't use Julia, but I've heard you can, on the fly, just there at the prompt, you can actually inspect the assembly language that comes out of it. And for a systems guy like me, I think that's really cool, but I wonder if ordinary R users would want to do that, if there were such a feature.
I hope not. Right, there was an attempt. Okay, so you can print the instructions of the bytecode interpreter, right? And I was trying to persuade a student to implement a better debugger that would work at the instruction level, and the student wasn't good enough, so it never finished. But I hope that people will not have to do it. Like I don't have to do it myself actually when debugging. I debug a lot of things in R, usually packages. I spent several months debugging packages before we could switch the bytecode compiler on. So, and I don't remember I would have ever had to look at the instructions, right? I had to look at the machine instructions often. In the last 3 or 4 months, I had to look at the disassembly for the native code. Yeah, so I hope that users would never feel the need to look at the instructions.
So I think in Julia, you can inspect both the intermediate representation and the machine code. And the use of that feature is, you know, mostly for the equivalent of the people in R who develop C++ packages. You know, end users would not look at it. But for the developer of a package in Julia, these two visualizations are a way to talk to the compiler. You have to think about writing Julia code as a conversation where sort of you write the code that is the shortest and cleanest, and the compiler tells you, yeah, but I can't quite optimize that. And then you ask why, and it shows you, well, there's this variable that I don't understand, and then you sort of fix your code. So this is not something you would worry about unless you really care about performance. But it would be useful if you do, because then you don't have to write C++ code.
And then maybe something like compiler hints, might that be useful for bytecode?
So compiler hints depends, it depends if these hints are changing the semantics or not. And for instance, one of the hints that I think would be really nice to have is to say that a function is not lazy, doesn't take promises. But this changes the observable behavior of the program. So it's not a hint anymore, it is an instruction, which is fine, but you have to buy into that.
Yeah.
So speaking of compiler hints and laziness, I know, Jan, you've looked at a lot of kind of some of the bottlenecks in performance. And I know one of those is that R has a lot of features that maybe some people don't always use. And a couple of those that often come up are things like lazy evaluation and non-standard evaluation. And so one kind of issue potentially with that is lots of users may not use non-standard evaluation and lazy evaluation very much in their own code, but kind of another huge component of the R universe, and this is something that came up kind of among the panelists before we started this discussion, was pipes and the tidyverse, which makes a lot of use of non-standard evaluation. And so I suppose one kind of big general question is how much are things like non-standard evaluation, lazy evaluation, pipes, how much do these kinds of things bottleneck performance? And if the tidyverse, lots of users are using these kinds of tools in the packages that they use, if not in their own code. So is this kind of a large bottleneck to performance, even
for the kind of optimization we want to do, they are, significant bottlenecks, but removing them from 90% of the code would be fine. And that doesn't mean we can't support the 10% or the 1% that actually needs it. So every R program does require, laziness somewhere, every single one. But, in 1 or 2 places, in 100 places, not in a million. And, so compiler technology, if we had, for instance, an annotation that said this function requires promises, well, we can honor that.
I'd say it depends a lot on the sizes and shapes of your data. And if you're running a typical tidyverse computation on a reasonable number of cases, the lazy evaluation overhead is probably not all that significant. If you were to, because this is what you were going to write a little tidyverse chain or pipe chain that's running on data frames of length of 2 rows, and you run that on a loop 1,000 times, you're going to pay very, very heavily for that. One of the things that I've experienced in teaching with when people think about or looking at somebody posts on Twitter or whatever, hey, I did this in R and then did it in C++, RCPP, it was 200 times faster. Because R is such a high level language, it's easy to get into inadvertently using very high level things at a fairly slow scalar level in a loop. And yeah, you're going to pay through the nose for that. In moving from that to a C++ implementation, you have to go through a bunch of steps, getting rid of these high level things and going to lower level things that exist in C++, getting rid of higher level data structures, going to simpler ones. And then there's a final step of going from R to C or C++. Very often that first that stuff all the way down to, but before going into C++, it really gives you all the performance improvements that's worth having. The final step often isn't worth necessary, but people don't necessarily recognize that, especially if they do it all at once. But profiling will often very quickly tell you, this is taking that long. Oh yeah, I'm using something that does really complicated non-standard evaluation and things of size 2 many times. At some points.
I wonder if many people on Twitter who are complaining this is slow are even aware of the fact that there are profiling tools available to look into that.
I'm pretty sure it's not used anywhere nearly as much as it should be. Our studio does make it have an option and a whole menu for doing it, and I don't care for the visualization they have, but the display, which is basically a hot path display, the text display is pretty good.
I mean, you don't see it in books, for example, as far as I know, any of the standard R books.
Doesn't yours have it in?
Well, other than mine.
Okay.
Mine doesn't have much, actually.
Okay.
Speaking of profiling and RCPP and things like that, another kind of common question that people will have with performance in R is, how do you know when it's actually a good idea or necessary to go from the R level to C, C++, or RCPP?
If the code runs for a week.
Well, and if a week is too much, right? So it should start with some external constraints, I guess. And then sometimes I think that it's actually hard to use the profiling tools like the R profiler that is inside because it doesn't tell you like where usually the analysis that people are running have some steps, some stages. I remember optimizing code from some people I got, and from the profiler I couldn't see which stage that was, and it actually helped much more to put print statements in the code. It's the most primitive way, of course, but just to find out which section of the computation takes more, right? So I think that this is often important to combine different profiling tools with the most primitive ones, of course, like these print statements. And oftentimes you find out that that even though you are using some things that are known to be quite slow in R, like function calls, or S4 is much worse than that, or non-standard evaluation. If you use them outside of the hot loops, well, that probably doesn't matter, right? So it only matters when the things take too long, and when the parts of the code that take too long use too high level abstractions, I would say.
The one thing the flame graph visualization in our studio is actually good at is telling you if you have a computation that has stage 1, stage 2, stage 3, it'll show you that reasonably well. So there are those tools in our studio, and it's in a package which I think is called ProfViz, but there's also the Prof Tools package that I have. So there's a lot of data collected, and there's a couple tools that you can use beyond just the primitive summary RProf to examine that. And it does require sometimes playing around with it to be able to dig down to what's there, but there is a lot of data there that can help.
But that's not answering Kylie's question, though, which is how does somebody know when it's going to be fruitful to go to C++ or C? The profiler will tell you where you ought to make that jump if you're going to make it. But, this is a huge investment of time to go to the C level. The profiler is not really telling you whether it's going to work.
It won't tell you whether it's going to work, but it does tell you whether it's worth trying.
Mm-hmm.
It might be worth trying.
The next cheap advice is to look for packages that implement some part of the code already in C, right?
Mm-hmm.
And then you can compare, obviously. Other than that, guessing if a part of code when rewritten to C would be faster, well, if it's some computational loop, probably it will be, right?
Mm-hmm.
But it's hard.
Norm, how often do you have to go into C or C++?
Almost never. Excuse me. For me, if I want to make it faster, I try to parallelize it. And I think, it's a big headache to go to C. And I say that in spite of, I've done a lot of C coding, but to go from R to C or C++, that's very daunting to me, frankly. I just don't have that kind of time.
I think when I was an R user, I never went to C, even though I could program in C. Of course, that was my field of study, right? And C++, I never did it. And sometimes I had simulations that ran for weeks on clusters, but I still did them in R.
Mm-hmm. Well, see, that's another issue that I think is interesting, is going back actually to my earlier question about, excuse me, how much need is there in the R community? Because I think there are a lot of people, who really are willing to let their code run for weeks rather than take some other drastic step.
So we have a question from the audience that kind of relates to that. And that's whenever this person complains about performance in R code, or whenever performance in R comes up, the response from a lot of people is to direct them to other languages like Python or Julia. And so I wonder if all of you have some thoughts on whether R is really slower than something like Python, or why, I guess this whole conference and this whole discussion panel, why is R actually slower than those? And if so, then why are we using it?
Well, first of all, I think the functionality is, again, it does relate. Functionality is typically more important than speed. Python is not fast, but you can you can vectorize in Python just like you do in R. But what you can do in Python is you can there's some dialects of Python where you can have a mixture of C and Python. There's one Cython and PyPy. I have not used them much at all, but that's the only way that I see that Python is faster. Now, I don't know, I may have to eat my words here. Maybe the person who asked the question has some timings, but Python's not fast.
Yeah, I think we use R for CRAN. If there was no CRAN, there would be no R.
The packages that have the value, right? For at least people coming from CS, as a programming language, R is not so interesting, right? It's a mixture of inconsistent features and so on. But it's so useful as an interactive tool for data analysis, and because of all the packages, that's the value.
So R is an ecosystem. It's not a language. The language is like, the little bit on top, but it's the you come for the ecosystem, the books, all of the questions and answers, the snippets of code, the quality, the quality of CRAN. Python doesn't have anything like that. You can dump a Python package in the world and maybe it runs. Maybe it runs in 6 months, probably not. No, but I mean this seriously. The quality assurance that CRAN brings is, we don't have that in any other language that I know of.
Well, it's nice to have a matrix type, though. I mean, not just, if you look at the language itself.
Sure. But on top of that.
Yeah, no, I agree with what you said.
Yeah.
But other than that, of course, R is slow, right? And it's not that we would be proud for how fast it is, right? And we would, of course, like to make it even faster. And this is what mostly Rjit has been doing in the bytecode compiler. And if we can do more, of course, we will do it. One of the things that are still very slow is the function call, for instance, right?
Mm-hmm. So maybe an interesting question to ask is, why is there a perception that Python is eating R's lunch in data science?
Well, it's not because of speed. It's to me, people use what they grow up with, and it's not even language. Why is the CS community eating the stat community's lunch in terms of data science? And there are reasons for that. They go back to money and things like that. And then the language comes out of that. You have a lot of CS people now doing data science, and they grew up using Python.
But that's not even true. So Python was not a popular language in CS circles until recently.
Right.
We were teaching Java, we were teaching Scala. No, what happened is, I think, is that there's this need for more software. And Python is much closer to the other languages that we teach in computer science. So the step to go from Java or whatnot to Python is very small. To go to R requires a very different way to think. It's vectorized. It has all sorts of features that you don't see in more traditional languages. So that, I think there's a part of that too.
Well, no, I agree that Python was, I mean, nowadays actually it's pretty standard in CS departments to use Python as the introductory
that's
language.
A new development in the last.
But it is new, I agree. But on the other hand, data science is new, and the two kind of happen together.
Mm-hmm.
And I don't, you know, I've seen a lot of languages. I don't think are as that different from the others. Maybe I'm missing something, but I think it's the same kind of thinking. I mean, now, you know, Luke mentioned Lisp. Now you're really talking about something different.
The vectorization is a big jump for many programmers. Everything being a vector operations and everything.
Mm-hmm.
But it is pretty natural when you're coming out of working with data in statistical context. It's more natural, which I think is why it arose through in the Bell Labs, and it was, after all, designed by statisticians back then.
But it wasn't natural in CS curricula, right? I was studying CS, and it was very math oriented, so I was interested in statistics and so on. But some people didn't take statistics at all, and they have never met any language that would be with vectors, right? I have used Maple and Mathematica, but I was different.
Mm-hmm.
To do things fast in Python, you still need to vectorize as well.
Mm-hmm. Yeah, sure.
So I often wonder myself where this conception of that Python is much faster than R came, because that's certainly not really my own impression.
So it always depends what you're measuring. If you want to do an algorithm that sorts a vector pointwise using a loop, Python will be 50 times slower than C, and R will be 500 times or 100 times, something like that. But is that the thing you want to do? Is that the thing you care about? Probably not. So, yeah, these abstract discussions of which language is faster, you know, we like to have measurables and metrics, but they're not really relevant in, you know, the day-to-day life of most people.
So what about the memory model? Instead of looking at speed, looking at memory usage and constraints and all that, maybe part of the perception of Python being better comes from that. What do you think?
So R is bloated, so there is a lot of memory usage. But I don't know.
But fundamentally, I mean, if you're working with base Python, you're still working with in-memory data. It's not like it's just, you know, SAS, for example, has been able to do some huge things because it's based on reading things off a tape, and so no, you don't keep it in memory. But that's not true. You could, of course, use libraries, packages that are based on out-of-memory computations in either one. Mm-hmm. But fundamentally, both R and Python put stuff in memory.
Mm-hmm.
And we do now, I believe, have real reference counting now. Thank you, Luke. So as we're getting closer to the end of this discussion, the few minutes left, I'd like to kind of ask more generally. We have a lot of new things in our recently, things like alt-rep are starting to get more use. We have these new reference counting to hopefully better handle memory. And so I suppose my more general question to kind of close things out as we get close to the end is, what's kind of the future for performance in R? How much faster can we get? How much How much performance can we squeeze out of it? What's the future look like for us? Kind of a big question.
You know, one question I'd like to ask, instead of answering yours, I'd like to ask one again to the group. What about GPU? I think a few years ago, John Chambers kind of dismissed the importance of it. And maybe for R, I think he may well be right. But that is one difference with Python, that Python seems to have been more aggressive in making things available at the GPU level. And I wonder what everybody thinks about that.
Well, there is a question whether it's there is a really big difference in the features provided or in how much they are presented, right? So Python has some packages that allow you to write code in a subset, in a meta language that is similar to Python that will run on GPU. But you can do, I was told you can do the same thing in with some packages that we have in R by Simon Urbanek, for instance, right? Like, correct me if I'm wrong, but my impression is that Python cannot offload arbitrary code to a GPU.
No. But the idea, I mean, the neural network stuff in Python, you know, it's become standard to allow backends either on the CPU or the GPU. And I'm not aware of any R package even on CRAN that does that. And maybe there's not a need for it. But I think if we're going to talk about speed, then that's certainly something that comes up.
But then at package level, right?
Yeah. Yeah, no, not something in R itself, although you know, I mean, the related thing is progress or lack of it on having an R compiler. You know, Duncan Temple-Lang's students have been working on that somewhat.
Yeah, I think that Jan got like 1,000 times farther in that, right? Duncan only started. He created some interfaces to produce native code, but it wasn't any close.
I think what we could hope for is something like Tomas said. Say you pick a restricted subset of R, some libraries, some operations, and if you write a function in that subset, we could offload it to the GPU and compile it efficiently. I think there's a matter of commercial investment. I mean, the amount of money that was poured into doing this for Python is you know, probably the income of a small country. So yeah, you know, like so there's sort of some realities there, but I think, yeah, if this is something that would be worthwhile, I mean, it is doable.
So we're just about out of time. I'd like to give each of you another chance to just have any final thoughts that you'd like to leave the audience with. Thank you so much for speaking with us today. So any final thoughts from our panelists?
Well, again, I would like to hear more from the R community as to how much of an issue speed is for them. And you know, I think we're kind of working blind here in terms of, you know, I mean, is there a problem to begin with? And if so, where is it and what might be done to address it?
Yeah, I would have a similar comment. It would be very useful to have realistic benchmarks. I have been asking for them for about 10 years, so I'm not very hopeful I will get more, but I will still try, right? So what is a realistic benchmark? Something that is computing, something that you really need to compute with real data that you can publicize, so it can't be anything secret. And it should be written in R, not in using some packages that are already offloading the computation to C. and it should be written in a way that intuitively is how one should write it. So a nice way without trying to optimize. And that would be great to have. And then we could profile it and try to have a look whether we can use it to hint how to improve our internals to run it faster.
Luke?
Yeah, I guess maybe I'll just close by re-emphasizing, make sure you get the right answer first and then time it. Oh, don't worry about optimizing unless you know it's worth it. Use profiling to figure out where you should improve it and go from there.
Thank you. I'm definitely always surprised by how much performance I can get just out of base pure R by looking at profiling. Jan, any final thoughts?
I think it would be great to support some form of annotations that could allow us to specify, for instance, types or whether a function needs lazy evaluation. I think that's something that's available in Python and that is well, that they've used well there. And I think we're trying to prototype some ideas how to do it, but I think if that would be one way to advance the language.
Excellent. All right. Well, I'd like to thank all of you for joining us for this discussion. Thank you so much to all of our panelists coming from wildly differing time zones. So I definitely learned a lot, and I hope that all of this was useful to the audience too. So thank you again. And I think that's everything that we have time for.
And before we end, for sure, first and foremost, thank you to all panelists, and thank you especially to Kylie for moderating the discussion. And I am amazingly grateful to Tomas. Tomas did really his best to coordinate this panel. He was pointing potential panelists. So Tomas, thank you very much for that. Your help. You really shaped this panel, and we are really grateful for this great discussion that we have thanks to your ideas. Thank you. And we are also very grateful to all of our panelists, including especially and highlighting Jan Vitek, who is a keynote of YR 2020. You can find his presentation on YouTube. Jan is also active participant of the Slack. I noticed some of the questions like related to PQR and so on the YouTube channel. I will repost them if you are not using Slack. I will repost these questions just after the conversation to the Slack. So they will be probably answered then in a written form by Jan. So, and remember, tomorrow we are meeting at 11 a.m. GMT +2 to hear a keynote from Roger Bivand. Thank you very much. Goodbye.
Bye.
Bye. Bye-bye.
Thank you. That was awesome, really.